Yeah, so it's my pleasure to introduce Sándor Kovács, who's going to talk about the injectivity theorem for Du Bois singularities. So please.
Thank you very much. Thank you for the invitation. It's great to be here. I met Karen about 30 years ago, about 2 months shy, I think. And so when I was preparing my talk, I started writing out what I would say about Karen. And then I got to 6 pages. And I decided that maybe I'll say it another time, or just to her. But I want to say that I still remember the moment that I met her. And I think that described a great quality of hers, which is enthusiasm. And it affects you. You become enthusiastic when you're around her. And also her curiosity. I don't think I've been to a talk that Karen was there and she didn't ask a question. And I think it's fantastic. And I don't know if I'm sure you noticed this, that sometimes she asks questions that she knows the answer to, but she thinks that there are people in the audience who don't. And so it's kind of like a community service. So thank you, and it's great knowing you. Okay, so okay, I'm just gonna talk a little bit more about it. So we were postdocs at MIT, and you know, we became friends immediately and started to talk about math all the time. And our backgrounds were quite different. So we kind of taught each other what we knew. And I think it actually affected both of us in a positive way. And for example, I learned about F singularities and such, and how they correspond to MMP singularities. And then at the time, I was fascinated with Du Bois singularities, which at the time wasn't very well known. I knew it because my advisor had a conjecture about that. He recognized the importance of Du Bois singularities and how it is important for moduli theory. So we talked about that, and then, you know, we kept talking over the years. And at some point, we realized that we always talk about math, but we don't have a joint paper. And then, fortunately, we actually changed that. So we actually wrote a paper together, which is also joined with Carl Schmidt, who was my student and then Karen's postdoc. And it's about Du Bois singularities. So maybe it's
and F injectivity.
Exactly. So it kind of through, you know, it became our original discussions manifested in that. So I'm trying to use this to justify my talk today, that it's about Du Bois singularities, which is kind of related. So by now, Du Bois singularities are relatively well known, but there may be people in the audience who don't know, so I will quickly review that. So we start with Hodge theory, and that one way of looking at the Hodge decomposition is via the Hodge-de-Rham spectral sequence, which the core of it is this resolution of the constant sheaf C by differential forms. So for now, let X be smooth.
Over C.
Oh, right. Thank you.
Your next company.
Well, I have C here, but this is actually something that I always forget to say. Okay. Yeah, I guess in this talk, it's important to say. Anyway, so we have this resolution. So we can think about it that in the way that this is a complex, and this is a quasi-isomorphism, or an isomorphism in the derived category. And this is a filtered complex. And that filtered complex induces a spectral sequence. That's the Hausdorff spectral sequence, which degenerates. So we have an E1 spectral sequence. That actually computes the static cohomology of X, and this degenerates at E1. And this is actually a fantastic result, because this side is algebraic, these are coherent sheaves, coherent cohomology, and this side is totally topological. So it connects these two words. Now, if X is singular, then this doesn't work that well. So but there is another complex which came from, so Dubois building on Deline's work defined a complex that I won't write it out like that, just denoted by omega x underline, which actually has all these properties. So okay, maybe I'm gonna be lazy, and what I'll do is just okay, I was gonna underline this, but then that wouldn't be actually correct. So this is also a filtered complex, and the associated graded. So we take the associated graded and shift it. So essentially, we get the analogs of these sheaves. But these are no longer sheaves, or usually not sheaves, just complexes. But it turns out that pretty much everything cohomological works the same way. So, for example, we do get an E1 spectral sequence if we add a few lines there, and it also degenerates at E1. So formally, it works the same way. And in addition, you have a natural map from the usual theorem complex to this one. So this one is formally the same thing, but the terms are not locally free sheaves, so it's kind of ugly. And this is a filtered morphism. So that means that we actually get induced morphisms of the associated graded, and this leads to, is this part visible on Zoom, or?
Yeah.
Okay, so maybe I'll put the definition here, just to save board space. So the definition of Dubois singularities, which is due to Steinbring, some people say should actually be called Steinbring singularities, but I think that ship has sailed. He said, let's say that X has Dubois singularities, or I'll just write dB. If the map when p is 0, so of course omega x 0 is just O. If we have a map from OX to omega x 0, then this is a quasi-isomorphism. Okay, so that's the definition of the Bois singularities. And just want to make sure that I do everything that I planned. Now, when I learned about this, I was a little bit confused of why we stick to 0. But I thought, okay, I don't know enough Hodge theory, and Steinbeck knows a lot more, so he knew better. But it turns out that actually one can make a similar definition for all P's, and it actually makes sense. So these are called higher Dubois singularities, but the actual defining it only happened about 40 years later than Steinbeck. I'm not totally sure whom to, okay, so I'm gonna put a lot of names here. So the notion actually first appeared, as far as I know, in a paper by Gustaza, Olano, Popa, and Vitashek. I think it was about 21, so indeed 40 years there. But the name only came in a subsequent paper by Jung, Kim, Saito. Looks like you have to have 4 people on a paper to do this. In 22. And it's basically saying that X has m Dubois singularities. If this map is a quasi-isomorphism for every P not larger than M. So if you haven't seen this, there will be an adjustment to this. I'm just telling you that this will be a little bit adjusted a little bit. If this is an isomorphism for the at most M. Now, if you look at their papers, they usually call this K Dubois or P Dubois. I'm actually advocating for M Dubois. The reason is that later on, Friedman and Laza also defined K-rational singularities. If you try to find literature on K-rational singularities, good luck, because if you write in K-rational in a search engine, it will give you rational points over K. So I don't think K is a good choice. P is not a good choice because we want to use P for the unrestricted variable. So for the restrict, I mean so I'm just spreading the word that it should be called M Dubois.
And there is a notion of K-rational singularity also, right?
That's right, yes. M rational. That's more important, but it would be weird to call it K Dubois and M rational. Anyway, this is not crucial, but I just wanted to put a bug in your ear. So next time you see someone calling it K Dubois, you can say, isn't this M Dubois? Okay, so now it turns out that both of these groups only looked at, so first they looked at hypersurfaces and then LCI singularities. And it turns out that in those cases, these sheaves actually behave a little bit better. But if you want to extend this for non-LCI singularities, then it becomes very rare to actually satisfy this condition. So another group, only 3 people, made the Shen Venkatesh, not the Venkatesh you might. And Wu said that if X is non-LCI, this is too strong. And they suggested that, well, one of the essences of Dubois singularities and M-Dubois singularities is that this sheaf that we don't really, or sorry, this complex that we don't really understand is really just a sheaf, right? So that's kind of 90% of the usefulness of this. So they said that, well, that in other words, so kind of this is the adjusted definition. They said that let's require, so let's say that X is M de Bois if this complex is constant in 1 degree. And then we can say, well, there's this guy, the zero cohomology, and in this definition, we're saying that it should be omega xp. They're saying, well, let's ask that this is relatively nice. So let's say that this is reflexive. And also, just for a good measure, let's say X is semi-normal. It turns out that in the LCI case, if this holds, then both of these conditions hold. So lemma is that if X is LCI and 1 de Bois, according to this definition, then H0 omega X phi is isomorphic to omega X. I should say M de Bois with M positive, then this is true for E. So in other words, if you take this definition and add LCI, then we get the original definition. And what else?
So can I ask why Saito's definition is too strong?
I'm sorry?
So why is Saito's definition too strong? Just to very clear.
Because, for example, at the moment, there isn't a known singularity that satisfies that that's not LCI. I secretly tell you that I actually just found one 2 days ago, but it's not known yet. Oh, God. Okay. Anyway, but if you look at the board now, there are 2 competing definitions, so we have to change this. And so they suggested to call this strict M de Bois. Okay, and actually it turns out that in a lot of proofs, we don't really need this, we only need this. So they also suggested that this should be called pre-du Bois, pre-M de Bois. And my personal take that maybe reflexive is not the best choice if X is not normal. One could go with S2 and torsion free, which if X is normal, then it's the same thing. But I haven't seen an actual example where this distinction matters. So I don't know if it does. Anyway, so that's the definition.
Sorry, just to clarify, so you don't have the codimension condition.
Oh, yes, thank you. I keep forgetting that. Okay. Right. So okay, I totally blocked this out in my mind. So this talk has just now became not entirely correct. Their definition included an additional codimension condition, which is needed to be, for this to be true. So to be compatible with the LCI definition. I really dislike this codimension definition. And for a while, I tried to convince all of those people, well, all of those and all of these, to not include that in the definition, but then they convinced me that there are actually published papers that just say M de Bois or K de Bois, and they would become incorrect or inconsistent. So I'm kind of agreeing to the, I mean, so we have to add that codimension condition, but I think it's worth studying this without that, and I
Call it M
suggest
steam brink.
I'm sorry.
Call it M steam brink.
Ah, well, I call it weakly ambiguous. So, so if you drop the codimension condition, then we'll call it weakly ambiguous. So my title should have been the injectivity theorem for weakly ambiguous singularities, but it does imply it for ambiguous because it's. Yeah, I'm not telling you the codimension condition because I don't remember the exact thing. It's something about the singular set has at least codimension 2m plus 1. Okay, Carl is saying it's approximately.
Yeah, I don't remember either, but yeah.
Okay.
It's on that order,
Yeah.
It's a condition on the codimension of the singular locus.
That's right. So it's a codimension. It's a condition on the codimension of the. So it's basically in the LCI case, for it to be reflexive, you need the codimension of the singular set to be at least 2. That's kind of a. Actually, maybe we could just assume. Okay. Okay. So that's that. I should go on. Right. Okay. Now on to the injectivity theorem. So just a couple of notation to make it simpler. So standard notation is omega x dot stands for a dualizing complex. And probably I'm gonna assume that it's a normalized kind of, what you would write down as a dualizing complex, but I'm not gonna get into too much detail. Probably there aren't too many people, but if you're not familiar with dualizing complex, assume the axis is Comacaulay. This is just a dualizing sheaf properly shifted. Okay? But then we want to introduce an object which is the Grothendieck dual of the dual complex. The rationale behind this notation is that this guy trivially is the Grothendieck dual of itself. Well, or sorry, the Grothendieck dual of OX. Okay? And now that means that sorry, this is not done, this is 0. So as we know, there's a natural map from O to omega x 0, and that means that using duality, you get a natural map between the duals. And then the injectivity theorem, in this case, I was doing this digitally, I could just circle this and push it a little bit down. We have to rewrite that. So this is a joint result of Carl Schmidt and myself. So we have this induced map, and so that induces maps on the cohomology sheaves. And the theorem is that this is injective. And there's no assumption on X, so it's on the singularities. So which is very important for the proof, and will present difficulties in the higher hierarchy. So so we have this,
So
and
there's
then
nothing at all on
I'm
it?
sorry.
Nothing
X
at all
is
on it?
Dubois, right? X is Dubois you're assuming, right?
So it's
Well,
could be
the objects have to be
a
defined.
non-reduced scheme.
Yeah, works non-reduced.
It works on reduced.
Wow.
The non-reduced case, we originally only stated it for reduced, but the non-reduced case was, sorry, I know the names, I just have to put them in alphabetical order. Ma, Shri, Shimamoto. So they checked that this actually works for non-reduced. Now, it's a little bit tricky because the Dubois complex for non-reduced is the same as for the reduced. So it sort of, it changes this, but it doesn't change that. Anyway, so once you actually step into these higher realm, you could ask, is there something similar for P? So let's say, so we have this map. Now, okay, so all right, I'll adjust this a little bit later. So we have this, and no, actually, let me adjust it now. So because of this modified definition, I want to replace the omega xt with this guy, and so I don't have to write that much. I'll denote this by omega xt widow. And it's obvious that there's a map, right? Because this is the H0, the zeroth cohomology sheaf, and there are no negative cohomology sheaves. So there's a natural map there. And then we want to do the same thing. So let's define, okay, I'm only defining this for this talk. So if you don't like the notation, it's not gonna be there for long. But so omega x p underline is the Grothendieck dual of this guy and omega x p widow is the Grothendieck dual. So basically just doing the same thing as that. And then the question is, if I, so now, obviously this map induces a natural map between these guys. And then the question is, if I take cohomology here, is this injective? And then, right. So, so I could ask this for every p. Now I will do something unforgivable and change this to m. And it turns out that maybe the right question is that if X has m minus 1 Dubois singularities, does this imply that?
And this is for all I.
Yes. And so maybe I should have done it this way, that this is actually a theorem of Mustafa and Popa. LCI case, so if X is LCI, then I'm just gonna say yes. Yeah. Okay. And you notice that because of this, if X is LCI, then these things are the same. So it's actually I think I actually don't need the I think it's true for everything because it just needs the collision condition and that's it. I'll go back to this.
Shall I ask a question?
Yeah.
Does weekly m divide imply weekly m minus 1 divide? The boy.
It's,
Does that, do you see what I'm asking?
yes, sorry, I put it there, I think, there, but I didn't put it here. So this is required for every p at most n. So it includes.
I see,
the
it's part of the definition.
Yeah. Actually, at some point, I thought maybe it would be worth looking at just that, but it seems that I don't know if it's a reasonable definition. Just assuming kind of something in the middle. So there is sort of a sense in.
There are examples where it's like 2 the boy but not 1 the boy.
No.
Weekly.
Well,
I mean,
I mean, if you make this definition, then no.
No, sorry.
I don't know, actually.
What you had originally.
So to tell you the truth, I gave it to a student to explore this, and there isn't anything that I can report on that. So it could
So
be
there's
either
not
way.
examples.
It could be something that's reasonable. It could be something like what you said that holds. I don't know any examples. We didn't spend too much time. But in the proofs, this is very useful, but it still makes things hard. So it's sort of, you know, so my main point of this talk is to actually tell you the difficulties in the proof once I get to stating the theorem. Yes.
Wait, is the lemma true actually? I mean, the H0 should be torsion free all the time, right? On the left-hand side. Even in the inside.
So Kuntz has a theorem that says that omega p is reflexive if the singular set is at least codimension 2.
Yeah, but do you really need the codimension condition?
Yes. It's not saying weakly Dubois. And that's why for weakly Dubois I might, well, there's, yeah. Yeah, so it does need the codimension condition. But their statement was for, well, it's an LCI and they stated it with that definition. Maybe I'm confusing people and I'm sorry for that. Okay, so you could ask this whether, so we don't actually know that this fails if this is not a set. Or at least I don't. And then, I don't know if anyone knows any of that. Okay, so they proved it for LCI, and then Shen and Wu proved it for as isolated singularities. And they explicitly stated this as a conjecture without either of these conditions. And so the result I'm reporting today is that this is okay. So just for X. But with this,
You're assuming m minus 1 to what?
I'm sorry?
You're assuming m minus 1 to what?
That's right, so X and minus 1. Actually, weekly and minus.
Weekly one.
Okay. So that's the theorem, and my plan for the rest of the talk is to tell you why it's hard to prove. Not the proof. Any questions before we get started? Okay, so
Sorry. So could you please remind when, after which point things become smooth? Like you cannot go much on end, right?
so that's with the codimension condition.
Oh, for that.
So with that, and Actually, Michna and I have kind of a disagreement on whether this is a good thing or a bad thing. And yeah, so so if you add the codimension condition, and then if m is larger than the half of the dimension, then the only thing that satisfies that condition is x is smooth. So I see this as an argument for not adding the.
Wait, can you say that again?
So the definition, with the codimension condition, if m is larger than half of the dimension of the dimension of x, then these conditions imply that x is smooth.
Oh.
I think I'm quoting that right. And you can view this as an advantage in the sense that if you have that condition, then you know that it's smooth, or you can argue that then if you remove this condition, then it still leaves a reasonable class of singularities to be studied. So I think both have, and now we have the weakly condition, so actually both can survive. Okay, so I kind of experienced the proof of this theorem as an obstacle course, that you run into something that doesn't work, then you fix it, and that makes you run into something else that doesn't work. So obstacle number one is that, so this degeneration of E1 implies that we have a surjectivity from the Barry cohomology to the cohomology. Well, actually, in this case, I can just write regular cohomology to OX. In fact, this surjectivity itself may be singled out as the main importance of the Bois singularities. That sorry, I'm making steps that I'm not telling you. So in here you just get this, right? So you have this degeneration at E1, so that implies that you have a surjective. So this has a filtration, and this is the top quotient in the filtration. So you have a surjectivity. And then if x has Dubois singularities, then this is actually the cohomology of OX. So you get the cohomology of OX comes from the Barry cohomology. And this has very useful consequences. But we don't have the same for P. And actually, when we want to prove, so here we're not assuming Dubois, or when we want to prove that something has Dubois singularities, then even this surjectivity with this sort of unknown thing is useful, because so we have this natural map, and this natural map actually factors through, the map from C to here factors through this one. So that means that this subjectivity actually factors through the corresponding cohomology of OX. So we actually get a surjectivity between these groups. Now the advantage of that is that that now we leave the realm of topology, and here we have complexes of given sheaves and the surjectivity between hypercohomology of that. But we don't have this for P. So this map does not induce a surjectivity because this omega xp is an intermediate quotient. So it's sort of, there is a surjectivity, but not from here. So if you, well, maybe I'll write it here. So we do have, so omega x is filtered. So we have these filtered complexes, And then by the definition of omega xp underline, there's a natural map that goes here. And then from the degeneration of the spectral sequence of E1, we know that this induces a surjectivity on hypercohomology. But we would like one from omega xp or from this guy. So, well, we have a omega x dot is also a filtered complex. And there are natural maps, but the arrows go their own way. So, this map doesn't factor through this one, unless you have an isomorphism here. But if you have an isomorphism, then you're already kind of where you want to be. So actually, just to point out, an isomorphism here is, so let's say for M, so this is isomorphic if and only if X has M Bois singularities or B to M Bois singularities. So this is a filtered morphism. So an isomorphism here is essentially asking, sorry, I wrote this, but I'm really thinking this. Right, so this definition, I could say this is equivalent to saying in that the format of the original definition that this natural map is an isomorphism for P at most ends. Now that, with this being a filtered morphism, for asking that that's an isomorphism for all P at most M is the same as asking that this is an isomorphism. Does this make sense?
I might have missed that, but what is omega tilde without the indices? Because here it's only defined.
Omega x p tilde is the H0, the zeroth cohomology sheaf of the omega x p complex. And it's relatively easy to prove that these actually form a complex.
Okay.
So that comes from the definition of this as the associated gradient.
I see. So just take the whole Bois complex and take the H0, and that is omega tilde.
No, take the associated gradient quotient. So we take the whole Bois complex, we take the associated gradient complex, shift it just so it's at the right place. That's omega xp underlined. And then we take the H0 sheaf of that. And from this definition, you can prove it relatively easily that these form a complex.
Oh,
that,
okay, I see. Okay.
And then the omega x little dot is that complex.
I see.
Thank you. I should have mentioned that. So does this make sense now? If it doesn't, you can ignore this. It's not.
Shift the P to back to the.
So the shift is just so that so when you have the complex, omega xp sits at the P place, and usually we just write omega xp. We're thinking that shift sits at the 0. So the shift just equalizes that. How long is this talk? An hour? Okay, so I have about 14 minutes.
20, I would say. You started a bit late.
Oh, okay. Oh, right, we did. Okay. All right. So, okay. So the problem is we don't have subjectivity to go on with, or we do, but it sort of it doesn't serve the purpose. But there's actually a subjectivity that comes directly from the degeneration of that, but it involves something else. So this guy. So this is a filtration. So this is a filtration. So this is kind of like a subcomplex of this, which I don't really like to say because we're thinking of this as an object in the derived category. So subcomplex doesn't make a whole lot of sense in the derived category. But there's a way to define this, or you can just think that this is another complex, then there's a map. And that works. And then FP plus 1 is yet another one that maps there. And then the associated gradient is really just the cone of this guy. So you can actually define all of these within the derived category. You don't need to work with subcomplexes. But in any case, I can take the cone of this. Actually, for later purposes, let me work with P plus 1 here. And I want to denote the cone of this F sub P. So in other words, this is a distinguished triangle. So what I'm really doing is, if you go back to the kind of classical case or the de Rham complex, then when you do this, this is the stupid filtration, which is start at omega xp and just take the complex from there. But then the quotient of that is taking the other part that go up to the missing ones. So this is why I actually put P plus 1. So if I start here with P plus 1, then this will go up to P. So this Fp omega x dot, this is really just OX omega x. So it's the sort of lower filtration. And I propose the name of co-filtration for this because basically if you take the definition of filtration and reverse every arrow, then you get that. Yeah?
Does the lower P have the kernel of the next term there? Or is it also just truncated stupidly?
It's just truncated. I think you would get that if you do the other, yeah. So there are these standard sequences. I'm just taking the separating. And this one, you can actually write down what this is if you know the filtration of this. But we don't need that. We only need that this is a quotient. Now, here's the observation that the even degeneration implies that the hypercohomology of this actually is the map on hypercohomology here is injective. Because when you have this degeneration, when you have this filtration, the filtration is actually given by the hypercohomology of the filtration of the. So you have a filtration of the complex. You take the hypercohomology of each piece. Those hypercohomology groups give the filtration of this cohomology group. So this is a very general thing that it just really comes from the even degeneration. In Haas theory, this is kind of derived from explicit knowledge of these things. So that means that this induces an injective map on hypercohomology, which means that this induces a subjectivity on hypercohomology. So if I replace omega xp with this guy, then I get a similar thing than what I have here. That the cohomology of C subjects onto that. So this implies that JXC, where this C is this is quasi-isomorphic to that. So the hypercohomology of this is the same as that. So this subjects onto AJ. Yeah. Now, why is this good? Because so this one didn't factor through that, but this one does. Because So we have actually a bunch of these complexes. And I can put the C here. So this is the usual theorem complex. This is the middle, the eight zeros. This is the Bois complex. And you know that this is a quasi-isomorphism. And so this subjectivity implies that, so when I map to FP, well, actually, what I should do is write another row. So I have FP omega x dot. And I have the lower t. Omega x middle. And FP. So now I know that this map is a quasi-isomorphism. And I know that this induces so this guy is surjective on hypercohomology. So I get that this composition is surjective on hypercohomology, but that one actually factors through these guys. So I get that this guy, so sort of not the FP version. So this implies that the hypercohomology of FP omega x fiddle subjects onto the hypercohomology of FP stuff.
Can I ask a stupid question? Do we really know that is a quasi-isomorphism that arc you have there? Because we don't have the cohomology 0 for all I, right? Oh, we do have it for all I.
No, this is the dot. This is dot. That's the Dubois complex. This is without assuming anything about singularities. That's how the whole thing starts. This omega x bar
Got it.
is quasi-isomorphic to C.
Okay, so that goes all the way back
Yeah,
to actually.
so
the
this
line.
line, so these four guys,
Yeah,
this doesn't mean anything. This is just
that's what Dubois proved, I guess.
that's the Dubois thing, yeah. That's the point of this complex.
Mhm.
And it's just fortunate that that the errors go this way, that it factors through these. I mean, the 0 one is obvious that it factors through that. Okay? So, and notice that if this P is 0, then this FP is really just the omega x 0 underline. Because, so F lower 0 means that we only go 1 or 0 step. We only have one driver. So you can consider this as the higher analog of this surjectivity. So for P equals 0 there, sorry, this surjectivity. So for P equals 0, this is what we get. Okay? So, okay. So we conquered obstacle number 1. That leads us to obstacle number 2. I need some room. So it's actually very interesting if you take our proof of the P equals 0 case. Formally, a lot of it works if we replace the objects with these. But there's one spot where everything breaks down, and so the problem with these guys, but for P equals 0, it doesn't manifest. But for other P's, this is not a complex of coherent sheaves. In the sense that, well, it is a complex of coherent sheaves, but the morphisms are not morphisms of coherent sheaves. So they're not OX module homomorphisms. So it's not in the derived category of coherent sheaves. It's in the derived category that's extended where the terms of the complexes are coherent sheaves, but the morphisms are only assumed to be K-linear, not OX linear. Okay? And the problem is, one of the things we use in that proof is Serre's vanishing. You can extend Serre's vanishing to some extent to complexes, but you need the morphisms to be OX morphisms. Because, for example, if it would work without anything, then it would work for omega x dot, and that's just quasi-isomorphic to C. I don't even know how to state Serre's vanishing for C. So it's unlikely that there's an NO. So most of the proof would work, but not all of it. I don't think I have time to tell you how exactly that's resolved, but there's another obstacle that I want to mention. So, which is sort of the resolution of that takes part in the resolution of this Serre vanishing thing, and so maybe that's out. So, okay, just for the record, obstacle number 2, Serre vanishing doesn't work. For FP omega x dot for the larger 0. Okay. Now, another issue is that if we're following the proof of in the n equals 0 case, then the proof proceeds by taking a cyclic color tangent along a general hyperplane section. And so we kind of have to compare these complexes on the hypersurface to X. And if you have, so if H is a general variable Cartier divisor, then we do have a distinguished triangle that goes like this. Which is basically the same thing that you get in the smooth case with taking a general hyperplane section. You know, there's a short exact sequence for omega, and then you can just take sorry, this is X. Maybe that's why some people looked.
But do you still want some log pole or?
I'm sorry?
So do you want some like log pole?
No, this is basically just, you know, restricting this to H.
Okay, so your notation basically means that omega p of x restricted to H, not omega p of H.
No, so it's not that. Okay, let me check my notes. All right. Oh, right. So it's important that this is general. So it's basically you take the sequence of OH, OX, OX minus H. In tensor, this is this guy. And then the claim is that omega xp tensor OH is this guy. And that works if H is general because then it's transversal to the hyper-resolution. So the hyper-resolution tensor with OH gives you a hyper-resolution of H itself. And so that shows that omega xp tensor, this L tensor is that. Okay? So it's important that this is general. So it's not the usual I know I said that. It's the usual. It's not. Uh, sorry. There are several sequences that need to be used, and those need to be used as well. But I just wanted to point out one. So basically, this obstacle number 3, if anyone is counting, so this obstacle actually appears several times.
So
but-
what is the obstacle here?
But I haven't told you yet. I'm building up the expectation. So this obstacle actually appears pretty much any time you have a distinguished triangle for these Dubois complexes. And the issue is that, well, if I have a distinguished triangle, then I have a similar map for the zero guys, the zero sheaves. But these don't form a distinguished triangle. When P is 0 and we're working with Dubois singularities, then this would give me, I would have OX here. For OX, this is actually a short exact sequence. But if P is larger than 0, well, I do get that this is injective, but this is not necessarily surjective. So, and you don't expect it to be surjective. It's basically, essentially, this would be surjective if this doesn't have an H1, but why wouldn't it have? So, and it's an H1, it's a sheaf H1. So just if I twist it with an ample, I can't make a sheaf H1 disappear with twisting it ample. So, so that really is an issue that. Now, if you assume that, yeah, so you could assume something that implies this, but not in general. Now, the resolution of this is that, well, I mean, this is sort of an auxiliary object. So what if I replace this with the cone of this map? Then I do get a distinguished triangle. But of course, if I want to use induction, if I replace this with the cone, then I also have to replace this with something else. So this actually works, but you have to start at the bottom. So you have to kind of replace everything there. So these omega riddles get replaced by something that's generally the same, but not entirely. Okay, I think probably my time is up. So there are more obstacles and more resolutions of that. But thank you for.
Sorry, this is more of a after this this that kind of question. So your theorem, does that help you prove higher version of card in the sense like higher if injective implies higher M Bois?
Right. So very good question. So I meant to mention some consequences of this theorem. So yes. So so the fact that you get an injectivity here very easily implies that higher M rational. So M rational singularities imply M Bois, or weakly M rational imply weakly Bois. And also, I wanted to point out. So this is actually, I think, it's a very important point that when we look at the Hodge theoretic knowledge that we get this E1 degeneration. Of course, I forgot to say that this is for X proper, but probably everyone knew that. But when you talk about singularities, you don't want to assume that it's proper, right? So the definition of singularity should be a local thing. So that's why we actually don't define Dubois singularities using this subjectivity, but something else. But so this requires X to be proper. Now this is a local thing. Even if X is proper, it's still a local because this is a sheaf. It's a sheaf, it's an injection between sheaves. So that kind of global surjectivity becomes a local injectivity. And that's kind of a very important usefulness of this. And then if you use matless duality, which note I learned from Karen about, if you use matrix duality, then this implies that there's a similar subjectivity for local cohomology. And the interesting part of that is that there isn't, this one is not there for local cohomology. So you can't get the local cohomology surjection from C. So you get it in this kind of iterative way that you have this subjectivity for proper, that implies this one for the sheaf, and that implies the subjectivity, just this one for local cohomology.
Can you say local cohomology of what?
Of these guys. So just put a
Small.
B here. Okay, maybe not B, small x.
So that always holds. That's not assuming Dubois or anything, right?
That's right.
Okay.
It's not assuming Dubois. So for
So can we state M Dubois in terms of
right.
local cohomology?
Okay, maybe I'll write it down here. So the corollary is that X has n minus 1 Dubois singularities, then for any X which M will subject so for m equals 0, this is a vacuous condition, so it implies Ux subjects onto it. There's a little bit of discrepancy here. I could put
Nicely.
well, okay, let's just. So you have that subjectivity.
So the higher ones.
Yes.
Are there characteristic P version of M Dubois?
I'm sorry.
Does there exist characteristic P version of
F injective.
Yeah, that's what
F injective is the
with
is there an F injective?
How many and with us?
Okay.
That is what I was asking, whether that version now proves what you proved, that should prove.
Oh, that was your
That should prove what car
your
was.
question.
Yeah.
I see. Okay. You should ask Carl and make sure.
How explicit, like if you just have a hypersurface or something nice, how explicit can you compute these
That's a very good question.
Dubois complex? I mean, I can write down the Durand complex.
Right. So for
The degree 0 1 you can do. I haven't thought about that.
right. So Carl has that.
You like, but by I do, I mean college who does.
Well, but so Carl has a theorem that says that the omega 0 part you can get by
Yeah, I remember.
embedding it into something smooth, to an embedded resolution of that in the bigger guy, and then the push order of O of the pre-image, so not the the strict tensional, but the entire pre-image. And this has actually a higher version, which is it's a little bit more complicated because it involves more than just just the actual term.
Yeah, I mean, yeah, the Durand complex is a little bit trickier because the maps aren't OX linear.
That's right, yeah.
So I don't quite know how to do that.
But Christine Hampton's thesis,
Oh,
she wrote down an explicit formula. I mean, it has actually, so it has input not just from P, but also from P minus 1. So it's not as clean as Carl's.
So maybe we could understand.
Well, I mean, if you understand embedded resolutions, pre-images of the thing that you embedded, and then push forwards of the round complex from that, then there's an explicit description. But I don't know how well you understand the push forward, derived push forward.
Mhm.
So it's and then, as I said, for getting the P term, you have to get information from more than just the P terms of that.
But like for a graded hypersurface or something simple like that, we can, with an isolated singularity, we can explicitly find an embedded resolution, just blowing up the vertex.
Oh, that, right.
I mean, maybe
right.
maybe we can understand it.
Yeah, maybe that. And also, the original definition is that if you take a hyper resolution, then this omega xp is essentially taking the omega xp on each term of that hyper resolution and then push it forward with the corresponding maps between. But I mean, I don't know if you would call that explicit. I mean, in some sense it's explicit, but it involves a lot of maps that we don't necessarily understand.
So I propose to continue during the break, so we can thank Chandra again, but I think you guys have an announcement too.